I don't have my book in front of me. I moved it over here. Grab it. Alright. Where do we leave off here? Oh, interesting. That actually did work. Okay, good status. Then chapter 03 problems. And we are on problem. We already did problem 315. Okay. Alright, let's continue onward. The jump instructions provide a means to implement conditional execution if, as well as several other loop constructs. Implementing conditional branches with conditional control. The most general way to translate conditional expressions and statements from C into machine code is to use a combination of conditional and unconditional jumps. As an alternative, we will see in section 366 that some conditionals can be implemented by a conditional transfer of data rather than control. For example, figure 316a shows the C code for a function that computes the absolute value of the difference of two numbers. Actually, it can return a negative value if one of the subtractions overflows. Our interest here is to demonstrate machine code, not to implement robust code. Okay, the function also has a side effect of incrementing one of two counters, encoding as global variables LT count and GE count. GCC generates assembly code shown in figure 316C. Our rendition of the machine code into C is shown as the function goToDiff.se. It uses goTo statement in C, which is similar to the unconditional jump of assembly code. Okay, let's go ahead and read through this. This is covered in the lecture. There's two globals here, less than count, greater than count. It's really greater than or equal, yeah, GE count. So we go into absolute diff, SE. Two longs. And a result long. If x is less than y, then we increment the count and we do the delta between the two. Else we do the delta in the other way. It's not really an absolute value, right? If x is less than y, so y could be -1, x could be -8. Okay, in that case, yeah, it flips it positive. Absolute diff, okay. X is 2 and y is 12. It also works. Okay. Evaluate goTo version. Or equivalent goTo version, sorry. goToDiff.se. So if x is greater than or equal to y, go to x GEY. Otherwise, we increment computer result and return. Yep. Generate assembly code. Yeah, I'm not feeling very creative this morning. Sometimes I have like an intense passion for wanting to learn about this stuff. but this morning I just don't. I do not. Kind of feels like a grind getting through this. Not gonna lie. I'm gonna go grab some aspirin because I have a bit of a headache. I think that's distracting me. Alright, this is the generated assembly code. So we have the absolute value difference implementation. Right at the top, it does a comparison of quad word RSI and RDI to see which one's greater than or less than. And it says if it's greater than, jump to, or greater than or equal, jump to L2. Otherwise, it does the bodies as we expect. It's a compilation of conditional statement. C procedure abs diff se contains an if-else statement. Generated assembly code is shown along with a C procedure go to diff se that mimics the control flow of the assembly code. I don't like these like C equivalents. I'd rather just have the original C source compiled into assembly and view the two. Using go-to statements is generally considered a bad programming style since their use can make code very difficult to read and debug. We use them in our presentation as a way to construct C programs that describe the control flow of machine code. We call this style of programming go-to code. In the go-to code, statement go-to xgey on line 5 causes a jump to the label xgey. Since it occurs when x is greater than or equal to y on line 9. Continuing the execution from this point, it completes the computation specified by the else portion of the function abs diff se and returns. On the other hand, if the test x is greater than or equal to y fails, the program procedure will carry out the step specified in the if portion of the abs diff se and return. Assembly code implementation first compares the two operands. Setting the condition codes. If the comparison results indicates that x is greater than or equal to y, then it then jumps to a block of code starting at line 8. That increments global variable ge count, computes x minus y, and returns the value as the return value and returns. Otherwise, it continues with the execution of the code beginning at line 4, increments global counter LE count, computes y minus x as the return value and returns. We can see then that the control flow of the assembly code generated for abs diff se closely follows the go-to code of go-to diff se. The general form of an if-else statement in C is given by the template if test expression, then a statement else expression, where a test expression is an integer expression that evaluates either to 0, interpreted as meaning false, or as non-zero, interpreted as meaning true. Only one of the two branch statements, then statement or else statement, is executed. For this general form, the assembly implementation typically adheres to the following form, where we use C syntax to describe the control flow. So we do a test expression, and then we jump. Then go to done. We don't have it done in the previous example because it's not necessary with the early return. Figure 316 shows an example of how we will demonstrate the translation of a C language control constructs into machine code. The figure contains an example of a C function and an annotated version of the assembly code generated by GCC. It also contains a version in C that closely matches the signature of the assembly code. Although these versions were generated in the sequence A, C, and B, we recommend that you read them in order A, B, C. That is, C rendition of the machine code will help you understand the key points. This can guide your understanding into the actual assembly code. That is, the compiler generates separate blocks of code for then statements and else statements. It inserts conditional and unconditional branches to make sure the correct block is executed. Practice problem 316. I think the biggest value I'm getting out of it is the freaking practice problems, because it actually caused me to have to like suffer and think a little bit. They were more rewarding than the reading and the lectures. When given the C code, void cond, short A, short pointer P, if A and dereference P is less than A, dereference P is equal to A. GC generates the following assembly code. So it's going to test quad word RDI and RDI just to set the flags. And then basically JE must look for the 0, right? We go back to our jump instructions. JE looks at the 0 flag, yep. So was the 0 flag set? The 0 flag was set because we're ANDing them with the test quad word. It's basically saying, are you 0? If you are 0, we're going to jump to L1. And then we compare RSI with RDI, dereferenced. That seems wrong. That seems wrong. The compare quad word takes RSI. RSI is the pointer, but we dereference the pointer, right, to get its value. We're comparing a memory dereference to a register, but I think these registers are wrong because RSI stores the pointer, RDI stores the value. I think that line is wrong. This comp quad word here, it just doesn't seem right to me. Jump less than or equal. Well, I guess it's the kind of the inverse, maybe. I don't know. Yeah, jump less than or equal. Otherwise, we move RDI into dereference of RSI. That would make sense. The comp Q doesn't really make sense to me, though. A, write a go-to version in C that performs the same computation and mimics the control flow of the assembly code in the style shown in figure 316b. You might find it helpful to first annotate the assembly code as we've done in our examples. Okay, doesn't seem too hard. Let's grab everything here. Boom, boom. That doesn't help. So we're just going to take the original function here, which should be valid C, yeah. And then we can do one of these. That's like that. Okay. Let's say if A what would we do? A not A. If not A, go to done. Down here, we're going to say, hey, done, return. Since it's void, I don't think we need a return. So we say if not A, go to done. Compare RSI, which is P, and dereference of RDI, which is A. I think they got their assembly wrong. Something like that. I don't know. Seems like a pointless exercise, to be honest. Alright, what is this? 316A. They said if A is equal to 0, or I said A, if not A, go to done. If A is greater than or equal to star P, your assembly's wrong. A is greater than or equal to star P, go to done. I'm going to stick with the less than or equal. Explain why the assembly code contains two conditional branches even though the C code only has one if statement. Well, first conditional branch is part of the implementation of the AND expression. If the test for A being non-null fails, code will skip the test of A greater than or equal to P. Okay, 317 or 316? 17, no 17. An alternate rule for translating if statements into goto code is as follows. So you get the test expression T. If T go to true, else go to done. Okay. Rewrite the goto version of abs diff se. Based on this alternative rule, can you think of any reasons for choosing one rule or the other? A, B. A will be, let's go back to here. It's called goto diff se. Goto diff, actually I can probably just copy it from here. This guy here. Oops, should grab the whole thing, right? So the first one has conditional jump followed by a jump. So both branches have jumps. It's either you're doing a conditional jump. So you pay the cost of evaluating a conditional jump and a unconditional jump. Whereas the first version, you have a conditional jump and then early return. I guess you could have the early return there too. The first conditional branch is part of an implementation. Oh, wait a minute, is this right? 317. This is an exercise to help you think about the idea of generating a general translation rule and how to apply it. Converting to this alternate form involves only switching around a few lines of code. So let's look at their code. They didn't split out the condition. Let's fix that. So we got go to true. And then do the return result there. Okay. So this is totally invalid. Seems like the same shit, right? Except the test is inverted. So it says can you think of any reasons for choosing one rule over the other? Maybe if In most respects, the choice is arbitrary, but the original rule works better for the common case where there's no else statement. For this case, we can simply modify the translation rule to be as follows. Yeah. Translation based on the alternative rule is more cumbersome. Alright, we're at 318 now. Starting with C code of the form test short. Okay. GCA generates the following assembly code. Fill in the machine expressions in C code. Okay. 1, 2, 3, 4, 5, 6, 7. God damn. Okay. So we initialize val, and then in every case we assign to val, and then we return val. Well, we're going to return to RAX, so we just got to find who's being assigned into RAX. These are all short integers. Okay. Looks like RDI, there's two things getting put into RAX initially. The load effective quad word, which is basically just doing some math on RSI and RDX. RSI and RDX are Y and Z. They're being added together. So Y and Z are being added together. Z plus Y, Z plus Y, and then RDI is being subtracted from that. RDI is X. So that seems to be like the initial. And then we have this comp 5 with RDX. RDX is Z, so we're comparing 5 and RDX is Z. We're assigning, we would be doing the test where we were to assign into it. So it would be Z minus 5, but it's not a subtraction. It's a less than or equal 5. Then we jump to L2, which is the return. No. Fuck. Well, I guess L3 also has a return. Alright, so this is going to be dot L2, I think. And this is going to be L4. This is going to be L3. L4. This is actually L2. Compare. So this is less than or equal to, so be greater than would be the comparison here. Less than or equal would then jump down to L2, which is here, which would be A, B, C, D, E, F. So L2, we're going to then look at that, and that's RDX in 3. RDX is Z. Something with Z in 3. And then we're going to jump greater than L4, if that's true. So this would be a not negation of that, which would be less than. Z is less than 3. Then we do that other junk there, which is, you just put it in here, which is move quadword RDX into RAX. So RDX be Z. So the value is equal to Z, but then RX is then divided by RSI, which is Y. Okay. And then if we go back up here, so I was taking that branch down to L2. If we don't take that branch, which means we're greater than, yeah. Then we go into another condition, which is 2 in RSI. RSI is Y. And then the actual thing is less than or equal to. We're going to jump to L3. I've already identified L3 as the down here. So we have to invert that and say greater than. Yeah, Y is greater than that. If that's true, then we do our jump down to L3. But before that, if it's false, we move RDI into RAX, which is X. And then we do an I divide with RDX, which is Z. And then the final one, which is L3, we move RDI into RAX, which would be X. And then I divide RSI with RAX, which is Y. Alright. Well, I think there's multiple interpretations here. So this is what? 318. The problem requires you to work through a nested branch structure where you will see how our rule for translate if statements can be applied. On the whole, machine code is straightforward translation of the C code. So short val is equal to x plus y minus z. Nope. It's z plus y minus x. Yeah, that's what I wrote. Z plus y minus x, that's correct. And then if z is greater than 5, and y is greater than 2, sorry, then x divided by z, yep. X divided by y, yep. And then else if z is less than 3, yep. Z divided by y, yep. I got it all right. First shot, 3.19. I think there's multiple interpretations though, because like for instance this jump here, so we're doing a comparison and then a jump, but then these two branches here are nearly identical, so they're interchangeable. So you can invert this less than or equal to be a greater than, and then just switch the order of the instructions here. So pull these down here and those up there, and it's completely valid. Because less than or equal is inverted from greater than. So it's really just the way the compiler decides to do it. And I decided to do it in a way that's sensible. But it can decide to do it any way it wants. By sensible, I mean like I labeled the else branches and did them in the same order as the compiler's output here. Alright. Moving on the reading. 366, implementing conditional branches with conditional moves. So this is something I'm less familiar with. Like the branching using like jump if equal, like all that stuff I'm pretty familiar with. But this stuff, the conditional moves, I'm less familiar with. The conventional way to implement conditional operation is through a conditional transfer of control. So you're modifying the instruction pointer, the program counter, where the program follows one execution path when a condition holds and another when it does not. This mechanism is simple in general, but it can be very inefficient on modern processors. An alternative strategy is through a conditional transfer of data. This approach computes both outcomes of a conditional operation and then selects one based on whether or not the condition holds. This is similar in theme to speculative execution, but with speculative execution, the CPU does it for you. So I wonder if this software innovation happened first and then that triggered a hardware innovation, or if it was the inverse. Like what came first? Did hardware implemented speculative execution, which inspired this technique in compilers, or did the compiler engineers implement this first? Probably the compiler engineers, because generally software moves faster than hardware. But yeah, it's only similar in theme though, because it's different in actual detail. So this approach computes both outcomes of a conditional operation and then selects one based on whether or not the condition holds. This strategy makes sense only in restricted cases, but it can then be implemented by a single conditional move instruction that is better matched to the performance characteristics of modern processors. Here we examine the strategy as it implementation with x86-64. Figure 317a shows an example of code that can be compiled using a conditional move. The function computes the absolute value of its arguments x and y, as did our earlier example, figure 316. Whereas the earlier example had side effects in the branches modifying the value either less than or greater than, this version simply computes the value to be returned by the function. So side effects force the compiler to not do this. And I think in the lecture he mentions like a GCC compiler flag that you can give it to also force it not to do this authorization. So the original C code, we just have our abs diff long if x is less than y, result is equal to y minus x, else result is equal to x minus y. Return result. Implementation of the conditional move in C. So we just compute our R val, and then our E val, and then N test, and then if N test R val, which is return val, is equal to E value. And then the generated assembly is a move quad word of RSI into RAX. So we just optimistically assign y as the result. And then we subtract our di from it, which is x. So the first branch is optimistically chosen for the return value. And then we put RDI into RDX. So we put x into RDX, subtract off of y to RDX, and then we do a comparison between RSI and RDI, which are our two arguments, which sets our flags, and then we can say conditional move greater than or equal to. So RDI is x. So based on that previous comparison, if it was greater than or equal to, meaning is y, sorry, if x is greater than or equal to y, then we move it in. Okay, that makes sense. It's the negation of the condition, which means the second branch should be taken, which means that we do the move. Okay, that makes sense. Compilation of conditional statements using conditional assignment. C function abs diff contains a conditional expression. The generated assembly code is shown along with a C function C move diff that mimics the operation of the assembly code. Boom, boom, boom. For this function, GC generates assembly code shown in figure 317C, having an approximate form shown by the C function C move diff shown in figure 317B. Studying the C version, we can see that it computes both y minus x and x minus y, naming these r value and e value, respectively, and then tests whether x is greater than or equal to y, and if so, copies e value to r value before returning r value. The assembly code for figure 317 follows the same logic. The key is that the simple C move greater than instruction of the assembly code implements the conditional assignment of C move diff. It will transfer the data from the source register to the destination only if compared quad word instruction on line 6 indicates that one value is greater than the other than or equal to the other, as indicated by the suffix GE. To understand why code based on conditional data transfers can outperform code based on conditional control transfers, as in figure 317, we must understand something about how modern processors operate. As we will see in chapter 4 and 5, processors achieve high performance through pipelining, where the instruction is processed via a sequence of stages, each performing one small portion of the required operations, e.g. fetching the instruction from memory, determining the instruction type, reading from memory, performing an arithmetic operation, writing to memory, and updating the program counter. This approach achieves high performance by overlapping the steps of the successive instructions, such as fetching one instruction while performing the arithmetic operation for a previous instruction. To do this requires being able to determine the sequence of instructions to be executed well ahead of time in order to keep the pipeline full of instructions to be executed. When the machine encounters a conditional jump, referred to as a branch, it cannot determine which way the branch will go until it has evaluated the branch condition. Processors employ sophisticated branch prediction logic to try to guess whether or not each jump instruction will be followed. As long as it can guess reliably, modern microprocessor designs try to achieve success rates of on the order of 90%. The instruction pipeline will be kept full of instructions. Mispredicting a jump, on the other hand, requires that the processor discard much of the work it has already done on future instructions and then begin filling the pipeline with instructions stored at the correct location. As we will see, such a misprediction can incur a serious penalty, say 50 to 30 clock cycles of wasted effort. Such a serious degradation of causing a serious degradation of program performance. As an example, we ran timings of the abs_diff function on an Intel Haswell processor using both methods of implementing the conditional operation. In a typical application, the outcome of the test x is less than y is highly unpredictable, and so even the most sophisticated branch prediction hardware will guess correctly only about 50% of the time. In addition, the computations performed in each of the two code sequences require only a single clock cycle. As a consequence, the branch misprediction penalty dominates the performance of this function. For x86 code with conditional jumps, we found that the function requires around 8 clock cycles per call when branching pattern is easily predictable, and around 17.5 clock cycles per call when the branch pattern is random. For this, we can infer that the branch misprediction penalty is around 19 clock cycles. That means time required by the function ranges between around 8 and 27 cycles, depending on whether or not the branch is predicted correctly. On the other hand, the code compiled using conditional moves requires around 8 clock cycles regardless of the data being tested. The flow of control does not depend on data, and this makes it easier for the processor to keep its pipeline full. Hey, it's noon. We got an hour in. That's good. Let me reread this. On the other hand, the code compiled using conditional move requires around 8 clock cycles regardless of data being tested. The flow of control does not depend on data, and this makes it easier for the processor to keep its pipeline full. Okay. How did you determine this penalty? Assume the probability of misprediction is p. The time to execute the code without misprediction is TOK. And the misprediction penalty is TMP. Then the average time to execute the code as a function of P is not sure I understand this. Okay, assume the probability of misprediction is P. So P is just the probability that it'll be mispredicted, like 0.5. The time to execute the code without misprediction is TOK. And the misprediction penalty is TMP. Then the average time to execute the code as a function of P is the T average of P is equal to 1 minus P times TOK plus probability of TOK P times TOK plus TMP, which is equal to yeah, because you go TOK minus TOKP plus TOKP plus TMP. So then you just get TOK plus PTMP. We're given TOK and T ran, the average time when P is equal to 0.5, we want to determine TMP. Substituting into the equation, we get T ran is equal to T average 0.5. And therefore, okay, that sort of makes sense. I don't think I would be able to do that on my own though. Like, I don't think if you just said, hey, we want to optimize this code, we think it's not predicting branches for these conditions very high, and we think that's hurting our performance. Being able to measure that, that's one thing. I'm not sure about how to go about doing that. I imagine there's some type of like CPU counters that inform you about your branch prediction misses. So that's one thing I would do is first measure if branch prediction is even an issue. And if it is, then look at benchmarking the performance with the branch prediction issues, and then trying to convert that into a conditional move, which the compiler is going to do for you if it can. But say the compiler can't, forcing it to do the conditional moves and then measuring afterwards, and then just empirically looking at the delta. I wouldn't try to like compute the delta based on some equation. I would just do it. As long as the cost of implementing is not too high, then I'll just do it and then measure the two. Wonder when the AI thing is gonna crash. Seems like we're getting close to it. It's a lot of promises that have been sold to people, and I'm sure they'll come true. It's just the matter of what timing. It doesn't seem like they're coming true immediately. Okay, we got a practice problem here, 319. Let's go ahead and start on that. 319. Running on a new processor model or code requires around 45 cycles when the branching pattern was random. Around 25 seconds where the pattern was highly predictable. What is the approximate miss penalty? 45 cycles when the branching pattern is random. And 25 seconds when the pattern was highly predictable. 25 cycles. The way I would go, I know they gave some equations up here that I could use, but the way that I would compute this is that, okay, 25 cycles, or sorry, 45 cycles is the average. And it's the average of three points, which is, or I guess 2 points, 25 plus x divided by 2. So we want to solve for x. So we get what, 90 is equal to 25 plus x. And then we get x is equal to 90 minus 25, which is equal to 65. So that means half the time you're doing 65 and the other half the time you're doing 25. And when it's highly predictable, you're doing 25. So the miss penalty is the delta between, this is the hit and this is the miss. The delta would be what? 65, so it'd be 60, 50, 40. 40 cycles. And how many cycles would the function require when the branch is mispredicted? That'd be 65. That's my simple math, not my fancy math. 319. Yay, I got it right. 40 and 65. Alright, it is noon. I've been on for at least an hour. And I think I should get some lunch. I have to go to the grocery store and do some shopping. I still have a bit of a headache. But when I get back, we continue on the conditional move stuff. There's some practice problems for that, and then we get into loops. So I will go ahead and hop off here. I'm gonna go grocery shopping, cook lunch, chill for a little bit, and then I'll get back on and hopefully get, let's see, it'd probably be 2:30. So I can get probably a good another 3 hours in today, but then I have a thing this evening I have to go do. So I will not be able to spend the entire day on this. Cool. I'll go ahead and stop here then, and I'll be back in about 2.5 hours, something like that.